Whether I'm audible?
Yes, sir.
Okay, thank you. So today we will discuss about the DFT, that is the discrete Fourier transformation, and the FFT concepts. Before starting the DFT, first of all, we will discuss some concept related to the Fourier transformation of the discrete time signals, that is named as the DTFT, that is a discrete time Fourier transformation. If we discuss here the discrete time signals, it means here we have to consider the sampling of the signal, and after the sampling, whatever is the signal, that will be transformed into the frequency domain with the help of the Fourier transformation. That's why it is named as the discrete time Fourier transformation. So here the continuous signals are just digitized using the samples, and during the time of the sampling we have to take care about the speed of the sampling and what is the value of each point of the sample here. And after the sampling there is a quantization, and quantization determines the value of the that is a particular value of that sample. Now, if we consider here the xt is a continuous time signal, and then we are interested in order to represent the sampled version of this continuous time signal, then it will be multiplied by a periodic sample pulse train here, that is the pt, and it may be represented as the xst is equal to yt, that is the summation of the k from minus infinite to the plus infinite xt del t minus kt. Here it means here the signal itself remains the xt, but we are considering only the discrete point of the xt in place of the continuum the interval. So here we are considering here the xt, and then it is shifted by the k times t, and k is ranging from the minus infinite to the plus infinite. Or this can also be represented here the x kt del t minus kt here. Now, if omega s is considered as the sampling frequency, then here the frequency domain representation of this one, that is the xs omega, that is the capital xs in frequency domain will be considered here. That it becomes 1 upon 2 pi x omega convolution with the here the shifted version of the this one, that is the delta function del omega minus k omega s multiplied by the omega s here. This may also be after some manipulation we can write this one as the omega s upon the 2 pi, that is equal to the 1 by t multiplied by x omega minus k omega s. Now here if we see, then we will find that if the here the wb is the bandwidth here, then omega s minus omega b must be less or equal to the wb in order to avoid the aliasing effect. So in order to overlap the spectrum of with each other, we have to follow this condition, and this becomes here the omega s must be greater or equal to the twice v, two times of the omega v. That is the here the sampling rate must be the twice of the bandwidth of the signal here. That is named as the sampling theorem, or the Nyquist rate of the sampling. And for example, if we consider here the 20 kilohertz here the audio signal, and if we are interested in order to store it using the CD here, so there is a need of the sampling, and for that purpose the sample rate is considered 44.1 kilohertz. This is the example of the sampling. Now, if we consider here the discrete time signal and its Fourier transformation, then x of the st, that is the sampled version of the signal, is nothing but the signal at the discrete points here, the x and t multiplied by e to power minus j n omega t. Or we can also represent this one as the x n z to power minus n here, and then we are replacing n of the t, then it is we are replacing here the e to power j omega n by the z. Z is replaced by e to power minus j omega. So z to power minus n will become the e to power minus j n omega t. And if we assume here that for the simplicity x and t is assume the x n and the capital omega is replaced by the omega of the t, then discrete time Fourier transformation may be represented as the x n e to power minus j omega n, ranging from the minus infinite to the plus infinite with the summation series, and inverse of the DTFT 1 upon 2 pi integration over the 2 pi interval x of the omega e power j omega and d omega. We know this concept, and it is the Fourier transformation of the discrete time signal here. And we can also achieve the Fourier transformation by taking the z transformation and then replacing the z by e to power j omega here. And it becomes the x of the omega and x of the n e to power minus j omega n with the summation series from the minus infinite to the plus infinite. This will be the representation of the DTFT. Similarly, the inverse of the DTFT may be represented by this one here. Now, if we are interested in order to represent the e to power j omega, then we know e to power j omega plus twice pi, this will become the e to power j omega. It is named as the periodic property or the periodicity of the function e to power j omega. And xn is a discrete signal. It means here what we are doing, we are just considering the discrete time Fourier transformation that is a windowed spectrum of the discrete signal here. Now, if we consider here the convolution, suppose we consider here the convolution, we are just going to use the convolution and the discrete time Fourier transformation during the time of the description of the DFT and the FFT. That's why we are considering the concept of the DTFT and the convolution. Now, if we come to this point, that is the what is the convolution, then if we consider the xn as a periodic function and that is represented with a non-periodic function, then this may be represented as the x a non-periodic function n. This is shifted by the k times n, and k stands from the minus infinite to the plus infinite, and this may also represented as the x naught t, x naught n, that is the non-periodic function convolution with the here the delta function, shifted delta function ranging the value of the k from minus infinite to the plus infinite, or this can be after some manipulation, this can be written in simple manner, that is the x naught n convolved with this function, that is the summation del n minus k n, and ranging from minus infinite to the plus infinite. Now, here if we consider the xn is nothing but it is a convolution of the non-periodic function with a periodic pulse trend Pn, and in the frequency domain it is the multiplication of both the spectrum here, and now this will be named as the spectrum of the signal x. And similarly, the Pn will be a summation from k is equal to minus infinite to the plus infinite del n minus kn, and that is a spectrum here. The in frequency domain, this will be the spectrum of the p omega, and this will become the 2 pi by n k from minus infinite to the plus infinite del omega minus twice pi k upon n. Now, if we see this one here, then we can say it is nothing but it is these are the spectrums, discrete spectrums, but separated by a integer multiplication of the twice pi by n. If the twice pi is the total range, then it is equally spaced by the twice pi by n, and we are considering the spectrum with a gap of the twice pi k by n here. So here the xn, this x omega may be represented by this one, that is the x spectrum itself multiplied by this one, that is the spectrum of the twice pn, that is the x naught omega, p naught omega, p omega, and p omega is represented by this one. This may be written as something like this manner, that is the 2 pi by n is a constant, so this will become the x naught twice pi k by n del omega minus twice pi k upon n. It is nothing but if we see, then we will find that it is its inverse will become here the xn, that is the 1 upon n summation k is equal to 0 to n minus 1 x naught twice pi k n e to power j twice pi k n upon capital N. This is the here the signal that has been received after the sampled version here. Now, if we consider here any discrete time Fourier transformation, then discrete time Fourier transform signal is nothing but whatever is the discrete time signal, it is multiplied by e to power minus j n omega, or we can say the discrete signal multiplied by z to power minus n, and then z is replaced by e to power minus j omega. Then we can say it is the discrete time Fourier transformation. And in frequency domain, in general, x omega is represented by this equation which we have discussed in the previous slide, that is the twice pi by n, having that x naught twice pi k upon n del omega minus twice pi k upon n here. Now, if it is a assignment for you that if xn is given by this one and mod of a, that is the value of the a is less than 1, then what will be the value when the mod of a is greater than 1? You have to achieve here the spectrum of the signal for this case when mod of a is greater than 1. Now we see discrete time Fourier transformation, having the some example have the signal. If we consider here that del n, then its discrete time Fourier dt ft becomes 1. Del n minus n naught, that is shifted e power minus j omega n naught xn is 1, that is a step function, it becomes twice pi delta omega, and mod of omega less or equal to the pi, that is the range of the frequencies from minus pi to plus pi. Similarly, we can represent e to power j omega n twice pi this one cos omega 0, and we are well aware with these discrete time Fourier transformations. And if similarly we can represent here the un pi delta del n plus 1 upon 1 minus e to power minus j omega n. Here again the range is from minus pi to the pi, and in order to get the un we have to use the signum function. Similarly, if we consider here the negative side of the un, then that will be represented by this one here. If we consider the exponential function a to power n un, it becomes the 1 upon 1 minus a e to power minus j omega, provided mod of a is less than 1. Similarly, if we consider the another range, that is minus of the a to the power n u minus n minus 1, and mod of a is greater than 1, then it becomes 1 upon 1 minus a e to power minus j omega. And if we consider here the a to power n un function itself, which we have described here, and it is multiplied by n plus 1, then it becomes 1 upon 1 minus a e to power j omega square, whatever was the value here, it's square. Similarly, if we consider here the a to power mod of n and mod of a is less than 1, its Fourier transformation becomes 1 minus a square upon 1 minus twice a cos omega plus a square. And we can also represent the another functions for discrete time Fourier transformation in the similar manner. And now if we come to the properties of the Fourier transformation, what are the properties? If the sequence xn is has the Fourier transformation of the x of the omega, x1 has the x1 omega, and x2n has the x2 omega, then in order to describe the periodicity of the xn, it becomes the x omega plus twice of the omega as equal to the x of the omega. Linearity that follows the law of the superposition and the homogeneity, a1 x1 n plus a2 x2n is the combination of the two signals. Then it becomes in frequency domain, it becomes the a1 x1 omega plus a2 x2 omega. Similarly, if it is shifted in time domain, that is the xn minus n naught, its Fourier transformation becomes e to power minus j omega n naught x of the omega. And if frequency shifting is taking place, that is the signal x omega is minus of the x omega naught, that is shifted by the omega naught here, it means equivalent value in the time domain becomes here the e to power j omega naught n multiplied by the xn. If we consider any conjugate of the xn, then its Fourier transformation becomes the conjugate of the x of minus of the omega. If we consider the time reversal, that is the n is replaced by the minus of the n, x of the minus n, its Fourier transformation becomes the x of the minus omega. Time scaling, if we consider here the time scaling, that is the signal is xm n, that is it becomes the xn minus n by m. If n is equal to the k times m, it becomes 0. When n is not equal to the k times m, then its Fourier transformation becomes the xm omega. And frequency differentiation, that is if we consider the differentiation frequency domain, that is the d by d omega of the x omega with the multiplied by the j, it represents in time domain n times of the x of the n. We also know that if we consider here the first difference of the in the time domain, that is the xn minus xn minus 1, then its Fourier transformation becomes 1 minus e to power minus j omega x of the omega. And if we consider the accumulation, that is the summation of the x k's, and k stands from minus infinite to the n, then it becomes a pi times x naught del omega plus 1 upon 1 minus e to power minus j omega x of the omega. And mod of pi is this pi, it means this omega ranges from minus pi to the pi here. Convolution of the two sequences x1n and x2n becomes the multiplication of the two sequence spectrum x1 omega and x2 omega. Multiplication of the two sequences in time domain becomes the convolution of the two sequences x1 omega and x2 omega multiplied by 1 upon 2 pi. And similarly, if we consider here the real sequence and xn has the two sections, that is the even and odd, then its Fourier transformation becomes the here spectrum of the real part plus j times of the spectrum of the here the imaginary portion here. Now even component x e n has the this real portion of the x of the omega, and here the odd component has the imaginary of the x of the omega multiplied by the j times here. The Parseval's relation is also represented in the frequency domain. It represents that if a relation, that is the x1n is multiplied by the x2n and ranges from minus infinite to plus infinite, it's in frequency domain it is represented as 1 upon 2 pi the integration over the 2 pi interval x1 omega multiplied by x2 minus of the omega d omega. Now the DFT, as we know, discrete time Fourier transformation is, it has a infinite range, and we can say it has a continuous representation of the signal having the e to power j omega. And for the discrete time processing, again there is a need of the discretization. So if the discrete time Fourier transformed signal is again sampled, then it becomes the DFT, discrete Fourier transformation. So here if we see DFT, then what is the DFT? DFT is nothing but whatever is the DTFT that is again sampled. And what will be the sampling rate? That will be sampled as that if the omega is frequency, then that will be sampled as the omega 2 pi k by n, and k will become here the 0 to n minus 1. So in place of considering all the ranges in finite range, we will consider only the n distinct sampled frequencies of the x naught n, that is the x naught omega, that is a non-periodic function here. So here the 2 pi space will be divided by n1, so these samples will be equally distributed, having a gap or the space of the 2 pi by n. So here now this xk, that is the DFT, is nothing but whatever is the discrete time Fourier transformation that has been considered at these values, that is the twice pi k upon n. So if we again consider represent this one xk, then it becomes the xn multiplied by w n k n, and k becomes 0 1 2 3 4 and so on. And now here the this w n k n, it represents the here the Twiddle function, and that Twiddle function has the properties of the periodicity and the symmetricity. Now if we exploit the properties of the symmetricity and periodicity, it means if this function is periodic, then same will be repeated after the n samples here. So if there is no need to consider again multiplication and the addition for the same sequences, but we will consider only for one period here. So using the periodicity property or exploiting the periodicity property, we can say number of the addition and multiplication will be reduced. And similarly, if we use here the symmetricity property, that is whatever is the sequence here, that the w n k n, this will be repeated after n by 2 sequences, but having the opposite sign. This is the symmetricity property. Again, the number of the addition and multiplication will be reduced when we are using this type of the property. So if we use this here, or we can exploit the properties of the symmetricity and the periodicity, then here the number of the computations reduces. And if the number of the computation reduces, then what happens? It means now this will become here the faster algorithm. So first, if we see the x of the k, that is the DFT will be finally represented something like in this manner, that is the xn e to power minus j twice pi k by n multiplied by n, where the k is from 0 to n minus 1, and the range of the n, small n, is from 0 to capital N minus 1 here. And we have assumed that e to power minus j 2 pi k n by capital N, it is a twiddle function, and it is represented as the WNKN. That is e to power minus j 2 pi by n. This will be represented as the Wn, and its power kn. So this will become the WNKN here. Now the x of the k is nothing but whatever is the discrete time signal x of the n, that will be multiplied by this total function, that is the WNKN, and k ranging from 0 to n minus 1, small n ranges from 0 to n capital N minus 1. Now if we see, then we'll find, if we consider e to power minus j 2 pi k upon capital N and its power n, this is nothing but this is equal to the WNKN, or we can say that it is the summation of the 0 to n minus 1 WKN. Now if we consider this shifted version of this one, that is the WNKL minus 1, then it becomes the capital of the n when the L is equal to n, and it becomes the 0 when L is not equal to 1, and if we consider here the summation of the WNK times L minus n here. Similarly, if we are interested in order to get the IDFT, then IDFT may be calculated something like in this manner, that is 1 upon n k 0 to n minus 1 x k w n minus kn, its power minus kn. So we can say, if we are interested in order to get the DFT, that is nothing but that is the sampled version of the DTFT, then that can be calculated, or that can be computed with the help of this equation, that is the summation series x n w n, its power kn. N starts from the 0 and higher range is the n minus 1. Small k is ranging from 0 to capital N minus 1. And if we are interested for the IDFT, then it becomes 1 upon n and summation x of the kw n, its power minus kn. K starts from the 0 to n minus 1. Again, small n is 0 to n minus 1. Now using these two formulas, we can calculate here the DFT and the IDFT. For example, if we are interested in order to get the 4 point of the DFT, then using the here the MATLAB command, we can derive this one, that is the x is the 1 2 3 4, so that is the input here, and for the k1 1 to n, we have to calculate the xk, that is 0, and for when the k is equal to k 1 minus 1, and we can use this do loop, this this conditional command here in order to get the DFT of the given sequence. Now, if we see here, then we'll find that if we are interested in order to get the here this is the n 8 point DFT, then we'll find n point 8 point DFT, and these are the 1 minus j minus 1 j 1 minus j minus 1 j, and these are represented here. Now if you see, then you will find, if we consider here the Wn, its power nk, Then if this is the value here, that is say 0 value, 0, 1, 2, 3. For the kn, if we consider kn as 0, 1, 2, 3, and again 4 comes here. So 4 and 0 are at the same location. It means it is a periodic function. Similarly, if we consider the 0, 1, 2. So if we consider 4 by 2, that is the n by 2, it is same whatever is the value here, but having the negative sign. The first property is the periodicity and the second one is the symmetric property here. Now if we consider the DFT, suppose the xn given by this equation, and that is the del n plus twice of the delta n minus 1 plus 3 delta n minus 2 plus delta n minus 3 here. That is for n is equal to 4, we have to find the DFT of this sequence, and by using the formula, that is the xn wn, its power kn, n is the 4 here. We put the values here, and n is equal to 0 to n minus 1, that is the 3 here. We will get here the 1 plus 2 w4k plus 3 w4 twice of the k plus w4 3 twice of the k here. So here the, and what is the value of the w4? It will become e to the power minus j twice pi by here the twice pi by n. So 2 pi by 4, it becomes j minus j pi by 2. So xk will become here the 1 plus twice e to the power minus j pi k by 2 plus 3 e to the power minus j pi k plus e to the power minus j 3 pi k by 2. Now, if we consider the xk, suppose these are the value of the DFT given as the xk is equal to 1 for k is equal to 0, 1, 2 up to the 7, and we are interested in order to get the IDFT, then we will utilize the formula of the IDFT. 1 upon n, that is the 8. N is and small n starts from 0 to capital N minus 1 w n its power minus kn, and we will put here the values, and we will finally get this is equal to the delta n. Delta n, that is its value is 1, that is just as small n is equal to 0 here. And here we have utilized this formula for the IDFT. Now for the first Fourier transformation, as we have discussed in the previous case, that in the first Fourier transformation, the number of the computation reduces, that is the number of the addition and the multiplication reduces. So the here the computational speed becomes faster. That's why it is named as the first Fourier transformation. So from the DTFT, we are deriving the DFT. That is when we consider the DTFT, and if we consider the sampled version of the, or sampling takes place after the DFT, it is converted in the form of the DFT. And in the DFT, if we are using exploiting the properties of the periodicity and the symmetricity in order to reduce the number of the complexity or the number of the multiplication and the addition, then it becomes the first Fourier transformation FFT here. Now consider the DTFT, that is the xk xn a w to the power kn, that is the DFT here. Then there is a need of the n square complex multiplication, and the additions which are required are n for each value of the xk. Now, if we consider here the n is equal to 2, for example, if we have considered here we have considered n is equal to 2 to the power 10, that is 1024, then n square becomes 2 to the power 20. Hello, हाँ सर, नमस्कार, नमस्कार सर. अच्छा, हाँ हाँ सर, हाँ हाँ, तो अच्छा सर वो उसका भी फोन So, okay, whether I'm audible? Hello.
Yes, sir. Yes, sir.
Yeah, PPT visible, no?
Yes, sir.
Okay. So we are discussing here the FFT, and in the case of the FFT, we have to utilize the here the properties of the symmetricity and the periodicity. So if we exploit these properties, that is the symmetricity and the periodicity, then DFT becomes the FFT here. And here we are trying, and we can say if in place of the n square complex multiplication and the here the n times of the additions, now in the 50 we can get here the actual calculation, that is the n by 2 log 2n. That is naturally very fast in comparison with the previous one here. So we see here how we can implement this concept here. The yk is nothing here. If we see, then we have to represent this computation, that is the FFT, with the help of the an algorithm, and that algorithm is named as the Radix 2 FFT algorithm. It is named as the Radix 2 FFT algorithm because we are considering those values of the n which are represented by 2 to power m, like that here. So this is if we assume here that capital N is equal to 2 to power m, this is called the Radix 2 FFT algorithm here. Now we can say yk is represented as the yn. If the yk is the output, yn is the input, and then yk is that is the DFT of the yn. Summation n is equal to 0 to n minus 1, that is the 2 minus 1, it becomes 1. Yn wn kn, and what is the n? This is the capital N is the 2, so this will become the w2kn, or we can say this will become the y0 plus w2k, and here the this value since small n is equal to 1, because the small n is equal to 0 to n minus 1, so this will become the w2k y1 here. Now this is the wt. What is the value of the wt? 2, it becomes the e to power minus j twice pi by n. N is 2, so it will become the e to power minus j pi, that is the minus of the 1. So we will get here the yk is nothing but y0 plus minus 1 to the power k y of the 1. Here the in the first interval, we can represent here the y. If the y0 is the input, then we will get here the y0 and y1 are the inputs, then accordingly we will get the capital Y0 and capital Y1 as the output here. And what will be the capital Y0? Capital Y0 will become the Y0 plus Y of the 1. So it will be written as the Y0 plus Y of the 1. जितन भाई क्लास में थोड़ी देर बाद, क्लास में जितन भाई थोड़ी देर बाद. हाँ हाँ, क्या टाइम दिया उन्होंने? तो ठीक है, उनको बता दीजिए वहां पर 4 बजे, फिर 4 बजे चलते हैं. हाँ हाँ, 4 बजे करेक्ट. ठीक ठीक. Now if we say here y of the 0 is y0 plus y1, y of the 1 it becomes the y0 minus y1. Here the y0 minus of the y1, in order to get this one, if this is the signal y0, we are getting here the summing point, it becomes the y0 plus y1, but at the same time we are considering here the minus 1. If it is multiplied by the minus 1, then this becomes the y1 becomes that the y0 minus of the y1 here. It is nothing but this is this can be represented as the y0 plus minus of the 1 to the power k y1, right? So here if we see this structure, then this structure looks like the butterfly structure. That's why this is also known as the butterfly FFT algorithm, having the 2 sequences, that is the y0 and the y1. Now in order to get the complete algorithm, we have to utilize the rules of the here the just divide and conquer approach. In this one, first we will break the xn into the even and odd portion. Suppose the xk is given and from n is starting from the 0 to capital N minus 1, x and w its power kn. It will be broken into the even and odd portion. For the even, we can consider here the small n is equal to the twice of the m, and for the odd twice m plus 1. So if we break this one having the even portion, and this one is the odd portion for the same one, then for the even portion, n will be replaced by the twice of the m, and so here it has also been replaced by the twice of m. In this case, it has been replaced by the twice m plus 1. And accordingly, the limit will be changed from m is equal to 0 to n by 2 minus 1, and in this case, m is equal to 0 to n by 2 minus of the 1. So now if we will we can represent now after this one, even and odd parts of the both DFT of the n by 2 sequences, break up this size n by 2 subsequent in half by letting twice m into m here. So here again, this can be represented in this manner. And now if we see wn twice of the mk, what will be the value of this one? It is nothing but this can be represented as the wn by 2 its power mk. How this can be represented? Because we know that e to power minus j twice pi multiplied by mk. This is the value of the wn m, and if it is n is replaced by the n by 2, so here this will become the this value is becomes the twice of this one, that is the twice time 2 times of this one. That's why twice of the mk, and this is nothing but it is equal to the wn by 2 mk of this one. Similarly, if we are interested in order to get the value of the wn by 2 m plus n by 2, then it becomes the wn by 2 multiplied by m plus wn by 2 its power n by 2, and here the wn to power n, it becomes 1. So this will become the wn by 2 its power m. So if any total function is can be considered as same value after the repetition of the n by 2, that is named as the symmetricity property here. wn to power n, it becomes e to power minus j twice pi I, and it becomes as value of the 1 here. wn to power n by 2, it becomes the minus of the 1 here. So these are the values that will be utilized in order to represent the FFT algorithm here. Again, we will represent the same algorithm, that is the xk is nothing but it has the 2 sections. The first one is the wn by 2 its power mk, ranging of the value of the m from 0 to n by 2 minus 1 multiplied by x of the twice m, that is for the even section. And similarly for the odd section, if we consider here the wnk as a common from this one, because this becomes the wn here the m has been n has been replaced by the twice m plus 1. So this will become the twice mk affects this one in the form of the n by 2, and plus 1 it has been taken common, so there is a term wn its power k, and summation m starts from 0 to n by 2 minus of the 1, this one here. And we know wn it's we have utilized this property here. Now this can also be represented in this manner, that is the xk is equal to 0. When the k is equal to 0, it becomes the m0 to 0, w1 its power m multiplied by 0, k multiplied by 0, x of the 0 plus w1 wnk, n is becomes 1 and w1 0 here, and this will be the summation m starts from 0 to 0, w1 0 multiplied by 0, x of the 1, it becomes the x0 plus x1. Similarly, the xk, when k is 1, it becomes the x0 minus x of the 1. The first one is x0 plus x1, the second becomes the x0 minus x1. Now the same result can be represented as we have discussed in the previous slide, that is the butterfly structure here. Now first find even and odd parts and then combine them. So if we are interested in order to get the Fourier transformation of any sequence, suppose there are the four sequences 0 to 0 to 3, then we have to combine them in bit reversal order here. How the bit reversal order takes place? See here, if the first output will be arranged in the proper sequence, that is the x0, x1, x2, x3 here, then we will consider its mirror image here, that is the mirror image of the 0, and it becomes the 0 0 0 here, that 0 0 its mirror image becomes the 0, 0 1 its mirror image becomes 1 0, that is the x2, and then 1 0 its mirror image becomes the 0 1, so this becomes the x1, 1 1 at the right side its mirror image remains the 1 1, so the x3. Now the sequences will be arranged at the input side in the mirror image form, that is the x0, x2, x1, x3. Means first we have considered here the even sequences and then we have put the odd sequences here. Now we know that is the if the x even k is the x even k and this is the x odd k, then accordingly we will get here the xk and the next higher value, that is the xk plus n by 2. And how it will be represented? In order to represent the xk, we have to consider whatever is the value of the xek plus x naught k multiplied by omega naught k here. And in order to get xk plus n by 2, we have to consider the xek minus times minus or times omega n k here. Or similarly, we can get here the 4-point DFT by using the formula, that is the f0, f1, f2, f3 here, by putting the corresponding value of the wn kn, that is the for the first row it becomes the 1, for the first column it becomes the 1, and for the remaining terms we can get here the values in terms of the plus j, minus j, and plus 1, minus 1 here. And then this will be multiplied by the input sequences. By using the matrix multiplication, we can get the same result, or by using the graphical representation, we can get the same results. So using any one approach, we can get here the FFT of the given sequences. Now suppose we have the 8 points and we are interested in order to draw the graph, or in order to represent the algorithm of, to calculate the FFT here, then first we will write here the FFT point in proper sequences, that is starting from the x0, x1, x2, x3, x4, x5, x6, and x7. And towards the left side, then we will draw the single lines here corresponding to each DFT here. And what will be the number of the stages? Since we are using the radius 2 algorithm, so for the 8-point FFT, the 8 may be represented as 2 to the power n, that is the 2 to the power 3. So there should be the 3 stages. So for the first stage, we will write here the sequences, that is the input sequences, and how these sequences will be written. In order to write the sequences, we have to consider the mirror image of the outputs here. So for the 8-point FFT, naturally the 3 bits are required. So here the 0 will be represented as the 0 0 0, and the mirror image will become the 0 0 0. Similarly, 1, the 0 0 1, its mirror image will become the 1 0 0, that is the 4. Here the 0 1 0, its mirror image will remain same, and the 3, that is the 0 1 1, its mirror image 1 1 0, that is the 6. Then 0 1 0 0, it becomes the 0 0 1 0 0 1, that is the here the 1, and 1 0 1, its mirror image becomes the 1 0 1, that is the 5. 6, that is 1 1 0, it becomes the 0 0 0 1 1, that is the 3, and 1 1 1, its mirror image will remain same, that is the x7 here. So these are the entries of the input side and the output side here. After putting the entries at the input side as well as at the output side, now we will consider here the combination of the two sequences here. Now for the, as we know that here this one is the lower one and this the second one will become the higher one. This is lower one, higher one, lower one, higher one, lower and higher. For the, in order to get the higher here the combination, it has to be multiplied by -1. So the here the higher portion will be multiplied by the -1, -1, -1 here, and we will draw here the butterfly structure here. So we will get here the butterfly structure, and the first one is the Wn Kn. Here this will become the and value of this one, that is that this one this power will become the n by 2 up to the value of the n by 2. For the two sequences n by 2 minus 1, that is the 2 by 2 minus 1, it will become the 0. So it has been written as Wn 0. Then by taking the values of the x0, x4, x2, x6, etc. here, we can get the values at these locations here. And after getting the values at these points, next is again here the total function will be entered. Total function will be entered. Now we will, and before considering the total function, we will consider the group of the four sequences. As in this case, in the first stage, we have considered the group of the two sequences. Now we will consider the group of the four sequences. And among these four sequences, the lower two sequences will be at the higher side. So for the higher side, they will be multiplied by the total function, and the total function range, highest range will become the Wn, its power n by 2 minus of the 1. And here we have considered 4, so n by 2, its power n by 2, that is the 2 minus of the 1, that is 1 here. So W40 and the W41. Now if we are interested in order to represent this one in terms of the 8, because the n is 8, so it may be written as the Wn, that W40 its square, and W41 its square here. So this will become the W80 and this will become the W82, or the Wn0 and the W82 here. And similarly, we will put here the -1 towards the higher side here, and we can get, now again we will draw the butterfly structure. That is, the lower side will be connected to the upper one in the butterfly manner here. The two sequences, two at the same time here, and the same is true for the remaining on this group here. In the third stage, the same will be done, but at this time we will consider here the group of the four sequences here. The four sequences, and now we have to consider the here the this total function that starts from the 0 to up to n by 2 minus 1. So here this will become the 4, that plus 4, that is the 8 divided by 2, that is 4 minus 1, 3. So the Wn0, Wn1, Wn2, Wn3, these are the total function here. And now we will consider the upper side towards the lower side, but in a group of the 4. So 4 points will be connected to these 4 points, and these 4 will be connected to the upper 4 side here. And the lower 4, that is lower 4 lines that is having the higher sequences will be multiplied by the minus of the 1, minus of 1, minus 1, minus 1, minus 1 here. So by considering the butterfly structure, basic butterfly structure, which we have discussed in the previous slide, we can draw the algorithm here, graph for the algorithm. And by this algorithm, we can calculate the final value, the value of the x0, x1, x2, x3, x4, x5, x6, and x7, and that will be the corresponding value of the FFT here. So in order to get the FFT, we will break the total n point into the n by 2, and again n by 2, and again n by 2, up to the value when it becomes a value of the multiple of the 2. Right. So first we have considered the sequences of the 2, the sequences of the 4, sequences of the 1, group of the 1 sequences, group of the 2 sequences, group of the 4 sequences here. And we will follow the butterfly architecture in order to describe the algorithm here. Here we have used some function of the MATLAB in order to describe how the FFT will be calculated, and we can calculate the FFT here because it will describe the spectrum of any design filter. So it will help us to design an effective filter. So this is about the DTFT, DFT, and the FFT, which we have discussed. That is the first, if the any discrete time signal, that is after sampling, if the signal is discrete time and we apply here the Fourier transformation, naturally we will get the DTFT. And if the DTFT signal is sampled, then we will get here the DFT. And in the DFT, if we again apply here the concept of the periodicity and the symmetricity in order to reduce the number of the multiplication and the addition, then we will get here the FFT. And for the purpose of the computation of the FFT, we have described the radix 2 algorithm, that how the FFT of the given sequences will be computed. So this is about the today's lecture. And if you people have any doubt, then please ask the question. Yeah, question please, if any query. So we are just